Hello everyone, welcome to this presentation on comparative evaluation of CNN architecture for brain tumor MRI classification. I'm Anushka and today I'll be presenting a study that compares the performance of the three popular deep learning models, that is VGG16, ResNet50 and DenseNet121, for classifying the brain tumors from MRI scans. So these are the content that I'm going to present, that is the introduction, related work, methodology, result and discussion, and the conclusion. Let comes to the part of introduction. Brain tumors are the serious and life-threatening conditions. Early detection plays a crucial role in effective treatment, but manual interpretation of MRI scan is both challenging and prone to the human errors. So, the deep learning models have been shown the tremendous potential in medical imaging. And in this study, we evaluate these three widely used CNN architecture, that is VGG16, ResNet50 and DenseNet121, to access their ability to classify the brain tumors using MRI image. So this is the problem statement. So here our aim is to explore whether we can balance the diagnostic accuracy with the model complexity and training efficiency. So the key research questions what are included. So I can say the first question is like that how to VGG16. Okay, so how to VGG16, ResNet50 and DenseNet121 compare in the classification accuracy. Then the second question is what is the impact of data augmentation and the fine tuning? Can this model generalize well to unseen data? And which model would be the best suited for clinical decision support? So now let's see the related work. Let's take a look at some related work. Okay, so in 121, researchers such as Wagmare, Salih et al. And Sumro et al. Explore the deep learning approaches for brain tumor detection. These studies confirm the growing adoption of the convolutional neural network in medical imaging and serve as a strong foundation for the current research. You can see all of the researches. Next, move to next slide, that is methodology. So here is all the methodology is given. So we follow the structure pipeline to evaluate the three model consistency. This is the pipeline structure. So first, all the MRI images were pre-processed by resizing to 224 by 224 pixel, normalized and augmented using the rotation, zoom and flipping. We initialized each model VGG16, ResNet50 and DenseNet121 with pre-trained ImageNet set. The classification, yeah, you can see here, sorry. The classification layer were customized and trained using ADAM optimizer. This is the one optimizer. And the early stopping and the model checkpointing were used to avoid the overfitting. Early stopping, yeah, both of them. Then the performance was then evaluated based on the several metrics like accuracy, precision, recall, F1 score, confusion matrix and the training time. We'll see in next upcoming slides. This is about the data set. So the data set used in our study include 7 2023 contrast enhanced T1 weighted MRI images collected from the multiple public data sets like Figshare, Raj and PR35H. So to ensure the diversity, the images were collected from the various acquisition protocols and the patient profile. They were categorized into the 4 classes. These are important, okay? So I'm now going to tell you the name of this. So the first one is glioma, then meningioma, then no tumor and pituitary. Now in the next upcoming slide we see the model architecture. Each of these three models like VGG16, ResNet50 and DenseNet121 has a unique architecture advantage. VGG16 is a simpler and faster to train. ResNet50 uses residual connections for better gradient flow. DenseNet 121 connects each layer to every other layer following the efficient feature propagation. So, all these models were fine tuned with customized classification head for our dataset. Now we'll go to the next slide, like model performance. Just see, this is a very important slide. Here we can see how these models are working and what its performance. So all three models exceeded 87% test accuracy. ResNet 50 stood out with the highest test accuracy of 88.33% and the highest validation accuracy is 89. Okay, validation accuracy is 89. VGG16 was the fastest to train but showed more sign of overfitting. And DenseNet 121 delivered a strong result but required more computational time. Then we'll see the confusion matrix. ResNet 50 delivered the most balanced prediction across the four classes. It had an excellent sensitivity, correctly identifying 397 out of 405 negative cases. VGG16 on the other hand produced more false negatives, especially for glioma and melanoma tumors. You can see here the confusion matrix result. And for DenseNet 121 perform well overall, but like VGG16 it sometimes confuse melanoma with glioma due to similar visual features. Now we'll see the training and validation performance. When comparing the training behavior, ResNet 50 covered the fastest and showed the lowest training loss at just 0.10, indicating the strong generalization. DenseNet 121 reached 96% of training accuracy and 85% of validation accuracy, but with higher loss. VGG16 had a significant accuracy gap, about 97% training versus 82% validation, which is clear sign of overfitting. Now quickly jump to the sample prediction. The slide shows example of both correct and incorrect prediction. All three models accurately identified the clear cases of glioma. However, they often misclassified glioma as melanoma. But this misclassification likely stems from visual similarities in tumor shape, location, or intensity, which even advanced CNN struggle to distinguish. Now come to the conclusion part. All three architectures perform well, but ResNet 50 offered a best balance between the speed, accuracy, and generalization. Its ability to minimize the false negatives and the achieve high sensitivity makes it specially suitable for real-world clinical applications. So this insight can help guide the development of AI-powered clinical decision support system. Now we'll see some references here. For those who are interested in further reading, here are the key references that are guided our study. These include the recent work on the deep learning application in brain tumor detection, transfer learning, and medical imaging technologies. Yeah, thank you.